the first two objectives have stars next to them, which means we already took the quiz on that. So I'm not going to worry about that stuff again. So we're just going to worry about the ones that don't have stars on them. That's the stuff that we haven't tested yet.
A lot of stuff.
It does look like a lot, but it's really, I mean, it's only 15 questions, so we're not dealing with a really long test here.
Shouldn't the one, the understanding applications of binary and stuff be
On the last one?
too?
Okay, so the applications of binary, octal, and hexal I didn't test on the last test. We talked about it in those lessons, but there wasn't any question that applied to the applications. You did like the binary questions, the skills on the first quiz, but in terms of like understanding what is binary good for, that was not on the first quiz. It was in those lessons, but it didn't actually make it on that quiz. So what are binary, octal, and hexa good for? What did we say was the primary application of those? Computer systems. All three of them are computer systems. Binary is the main computer system because with just a 1 and a 0, those represents offs and ons. Okay? But writing something out in binary takes so many characters that they want ways to condense that language, and that's when we go to the octal and the hexadecimal. And the reason why they use those is because octal and hexadecimal are both powers of 2, so it's easy to convert directly between them, not having to always go back to the base 10 and then make conversions. You can go directly from one to another. So binary works well for computers because ons and offs, and then the other ones just help condense that computer language. Okay?
So we're gonna need to make our like the 001.
No, you won't have to. I'm not going to test the skill of it, just the understanding of the application, right? This is applied math, so we always want to think about what is it good for. So that's what we're looking at here.
So we just need to write like.
There will be some questions that you're going to answer with words and sentences, yes.
So you're saying you could say like they're used for computers and yeah. Okay.
Yes. So this would be a question that would be answered in words and sentences, not in a math skill.
Okay.
So the next one says be able to, so that's where we're thinking more about skills. Be able to identify the structure of a system and which properties are true, whether it's a number system, a modular system, or a non-numerical system. So what were some of the properties that we talked about? I'll give you a first one, which may jog a memory. Closure. So closure was something that we talked about, like when we talked about our non-numerical systems, where we had like all the chart and we had all the letters in there. Okay. And we talked about closure. What does closure mean? How can I tell if a system is closed?
They're all the same.
Yes.
They're all the same letters.
Yeah, and there's no new letters that come up. So like in our chart, we're going to have certain letters or symbols over here, and you should have the same ones up there. And then whatever's inside of the chart better be the same stuff. Okay? So like if we just have A's, B's, and C's as our inputs, but we're getting an output of D, that's not closed. Okay? So in a closed system, all of the outputs should be inputs. Okay? What was another property?
Identity.
Identity. What does an identity do?
Isn't it where the letter like where it's the exact same as like ABC? So like under one of the letters it'll be like ABC, probably C in this case. Or something.
Yep. We're looking for which letter we can apply that won't change the problem. So just like with numbers, I can multiply by 1, and that's never going to change what it is. So we're looking for what can we apply that won't change the input. So in a chart, you would be looking for where the column matches the input. So then the identity in this one would be C, because it's under the C. Okay. So the identity is a number that doesn't change the input, and that'd be where we have some matching columns, where a column matches the original. It should also be true for the rows as well.
Another one is associative.
Associative. Associative is a whole lot harder to check for. What does the associative property say? Think about the word
Isn't it like a
associate.
diagonal thing? Is that the one?
Oh,
Different one.
The one where, like, it's the same on this side and on this side.
No, that's the diagonal thing he's talking about.
It's when you get like the C, what and what gets that C number where it's all the same. Isn't that what it is?
Not
Isn't
quite.
it like kind of like a reflexive property, like it doesn't matter which way you do the thing?
That's commutative. So associative we didn't do a lot of practice with because to test it you really have to test everything. What the associative property says is that grouping doesn't really matter. So like if we're talking about adding, that I can do like 1 plus 2 plus 3, and that's the same thing as doing 1 plus 2 plus 3. That moving parentheses around doesn't change the outcome. But for testing that in like a charted system, you would really have to work with a lot of problems and moving parentheses around with all of
So
them.
that's not gonna
So
be.
that one I won't test. I might ask you, what does associative mean? Associative allows for regroupings. Think about the word associative, sounds like associate. Okay, so who do we associate with or how do we group ourselves? And when is regrouping allowed? Okay. So one that you're mentioning with the forward and backward is the commutative. There's no N in there. Students always want to throw an N in there. It's not, I don't even know where they put it, like commutative or something. It's commutative. It's like a commute. It's the same thing forward and backwards. Okay, so like 2 times 3 is 3 times 2. Okay, the way we check for it in a charted system is the diagonal. Okay, so you guys are asking about the diagonal, or the flip side. We look at that diagonal, and if we could fold the paper on that diagonal and everything lines up, that's a commutative system.
Like, not exactly, or exactly lines up.
Exactly lines up. So if I have an A in that top corner, I have to have an A in the other bottom corner. If I have a B here, I gotta have a B there so it'd land on top. Okay. One other one kind of goes with the identity.
Okay, which way are you folding the paper?
Like
Up and down or like?
right on that line, right on that blue line. So diagonally across, yeah. So this A should match up with that A and the B should match up with B.
But if it was folded the other way,
On the other diagonal,
it would work the same as the
Yes.
other. So it
Yep.
doesn't matter.
both diagonals should work. So in this case, this one wouldn't work on the other diagonal because the B and C wouldn't match up. Inverse is like identity, but an inverse is what you do to get the identity value. So each letter will have its own individual inverse. Okay, so if our identity value in this one, I had a C, because that was where I made the columns match, then our inverse for a letter is what do you apply to it to get C. So if I had a C right in here, the inverse of B is A, because that's what gave me the outcome of that identity value. Okay, if I had
Oh,
a
so
C
you're
up
just going-
here,
Yeah.
then the inverse of A is B, because that's what gives me an outcome of that identity value. Okay?
Didn't they?
No, never mind.
Wait, hold on.
So like, it'll ask you, let's say like inverse of A,
Mm-hmm.
and then it would be C, right?
The inverse of A is B,
Why?
because that's what gives us an answer of C.
What was
Is it
like
gonna
But like, do we have
ask
C in the beginning then?
Yeah, you have to find what your identity is first.
Oh.
So you have to find your identity, and then the inverse is what, okay, so that sounded a lot more deep than it needs to sound. Hopefully we all know where our identity is found. In here, we have to find the identity for the system. And then the inverse is what gives an outcome of that identity value.
Somebody laughing at you. Find your identity. You can't do this class if you don't want to.
So I'm going to make you write an essay about finding your
I should have a
identity.
t-shirt for this class. We should
Have the guy who's like, with the figures like,
Yes, there's the guy who's like, I don't know what I'm doing, and then like it just is find your identity.
People did not understand that at all.
You really couldn't find your identity in applied math.
That's awesome.
So many numbers.
All right. So those are our properties. Any questions on the properties? All right. So then the next thing says be able to perform congruencies in modular arithmetic. So in that skill, I'm going to give you a number like 26, and I'm going to give you a certain number system. We'll say mod 5. You have to tell me what is 26 in mod 5. Because in a mod 5 system, we only have 0, 1, 2, 3, 4. So the number 26 doesn't really exist. So what is it the same thing as, and how do we do that?
I don't remember this.
I don't remember.
Wow, that's
Oh, wait,
Very
wait, wait.
good.
I know.
You just divide by 5.
Divide by 5,
1.
and we get a remainder of 1, and
It's
that's
like
the
clock
answer.
thing. It's just like
It's the
12
clock thing.
hours or 5 hours.
Yep. Yep, so on our clock for this one, we would have
This is
0,
not
1, 2, 3, 4. And so what we're going to do is divide it up in terms of how many numbers we have. We have the 5 numbers. And whatever our remainder is,
And
that's
that
the
works for
equivalence.
all cases like
That
that.
works for all cases of modular congruences.
This isn't as hard as I
Okay? So like if I gave you 32 mod 7. Okay, so we're going to take 32 divided by 7. The closest one that we can get in there is 4, but with a remainder of, we don't really care how many times it goes in, but 4 times 7 is 28. So our remainder would be, subtracting out gives 4.
This reminds me of those, like, when we did the 360 circles in whatever class that was, with the pie chart, or with the pie things, and then you had to change it to the radians and all that stuff.
Yes, yeah, so like in a circle, you have 360 degrees, but if I ask you to graph an angle that's 900 degrees, you have to think about how many 360s did I do, and then how much extra. And a modular answer is how much extra. That's just that leftover part.
So that whole time, we could just have been finding the remainder on our calculator.
Well, your calculator doesn't just give you a remainder though.
We had to find the remainder.
Right.
But it's so much, finding the remainder on your calculator is so much easier than like.
Oh, you mean when we were doing all the spirals? Yeah.
Yeah, and then calculating that up.
All right, understanding some applications of modular systems is the next thing. So with modular systems, the main application that we talked about was check digits. And how whenever you see like a long string of numbers that is in some way associated with a certain thing, so a shipping label, a driver's license number, a UPC code, a book number, those numbers all somewhere embedded in them have a check digit that validates that number. So I can't just make up a string of numbers and say that it's a UPC code. It wouldn't necessarily be valid. You won't necessarily need to find any of the check digits. You just should know that a major application of this is
Oh, we don't
check
even need to know
digits.
the divide by.
no, because it's every type of thing has its whole own process. So finding a check digit in a driver's license number is different than in a UPC code. So you don't need to memorize any of those processes or actually even need to be able to do them. Just know that that's what it's good for. Okay? The next one says be able to identify a prime number or perform a prime factorization. So that's what our last unit was about. The very last homework assignment was about that. So if you're given a number, you just want to look at trying to divide it by 2, try to divide it by 3, by 4, by 5, and so on. If you try up through 19 and nothing's going in there, we're going to just go ahead and call that prime, even though it may not be. But we're just going to kind of make that as our cutoff so you don't have to try forever.
Are we gonna have this little
The
box
chart? No.
thing?
No, of the shortcut ways of telling?
Oh,
No. But you'll have your calculator, right? So you can just
Yeah.
try dividing it on your calculator.
good point. Okay.
If we have time, can you show me that?
Yep.
That's prime set, 'cause
The next one says, understand how prime numbers play a role in computer data encryption. So we talked about in terms of that numbers episode, how what they do is they take lots of really large prime numbers and multiply them all together to get an enormous number, but somebody's not going to be able to make a factor tree for that. And that is where the security comes in, is somebody needing to know what those prime numbers are. Okay, so like in the episode, they showed like, you know, I don't know if this number is prime, but like 691 or something, it could be a prime number. And you take other like huge prime numbers and multiply them all together, which is going to make something enormous. And being able to break that down is how they encrypt computer websites.
Let's say in like 10 years, someone figures out that formula.
They'll have to
Who
figure out a
teaches
new
this
way.
lesson Totally different.
Oh yeah. Yeah, they'd have to figure out a new way to encrypt this. That wouldn't work anymore if they were able to not only prove the Raman hypothesis, because the Raman hypothesis in itself, just proving it, would be proving some sort of a rule about where to find prime numbers, but actually then being able to make like a step-by-step directions of how to do it is even something beyond that. But if they could do that, if somebody can figure this thing out, then internet security is going to have to totally change.
So, if they were to figure this out sometime between this right now and the next time we're in this class, would we have to take this part on our test?
Well, it's not going to happen tonight. So you have to take this part on your test. I don't know what's going to happen in the future. But this theorem has been around for like over 150 years. So I'm not actually even really that concerned about it being proven in my lifetime. I think this might be one of those unprovable theorems.
But if it was, and it was all over like the news tonight or whatever,
We would have a big happy party tomorrow if that happens.
you could bring like
Or a really unhappy party because now my bank website could be hacked. So that would be a problem.
Nobody has any money.
Alright, where are we in our objectives? Okay, so prime numbers, computer data encryption. Okay, so the next one says, know some of the major theorems involving prime numbers. So we had 3 of those theorems. So one of them was the Raman hypothesis, and that talks about kind of the spacing of these prime numbers. So they get further and further apart as we go, but it seems so far to actually be random. But the Raman hypothesis would be coming up with some sort of non-random pattern to it. But so far, it kind of looks random to us. Then we talked about the Goldbach conjecture. Anybody remember what the Goldbach conjecture said?
every even number can be written as the sum of 2 primes.
Awesome. So like 6 is even. So we should be able to write 6 as the sum of 2 primes, 3 plus 3. Okay. Remember, 1 is not a prime number.
Do you want us to just name them, or do you want us to explain them too?
You should know what they are, not just their names. So 12 is an even number, 5 plus 7. Okay, so you should always be able to find 2 prime numbers that can add up to an even number.
What
That's
about
what the
like
Goldbach conjecture
20
says.
or something?
20.
Oh, I thought you meant like, yeah, never mind.
And then the third one, the third big theorem about prime numbers is the one the article is about, which is about twin primes. And that theorem about twin primes says that twin primes are primes that are 2 apart from each other, so like 3 and 5 or 5 and 7, and they happen a lot in the beginning. And that theorem talks about the fact that they will happen infinitely. Even though prime numbers are getting further and further spaced apart, we should still keep being able to forever find these pairs. That kind of plays into Raman. Because if it's totally random, we might not be guaranteed to find these pairs. But the twin primes conjecture says that we can find these pairs, and that's what that article was about. It seems that that may have been proven now. It's still kind of under review. But it seems like that guy may have proven that twin prime conjecture that forever we'll keep being able to find these pairs.
Why did someone even make numbers this big, like when they were making number systems, like in the very beginning?
Why did someone make numbers this big? I don't know. You gotta be able to count forever. It's just a pattern, right?
It's strange.
So, I mean, the Egyptians didn't. They just said, like, I'm done.
Right.
Right? But I guess, yeah, I mean, in theory, we can just keep going forever. So, and then the very last one says, understand that numerical systems are one way that God shows order in creation because there's so many patterns in number systems. And that being able to actually count and do things with these numbers is part of us being made in his image. Because like squirrels don't so much count. Okay, they know like more acorns is better than fewer acorns, but they don't really like do things with that knowledge, right, other than eat. So something important about being made in God's image is that we can do this. We can think abstractly about those huge numbers and about the primes and something like that. Okay?
Are we gonna have to do, I don't remember
It's trees like
what, I think it was the mod lesson where it was like subtractions, so it'd be like.
Yeah, so you should not only, I guess, be able to perform congruencies in modular, but be able to perform arithmetic in modular. I guess it doesn't really say that as a bullet point, but it should. So being able to do something like 7 plus 8 in a mod 12 system. Okay, so there's two ways to do it. One way is to just do the arithmetic and then do the congruence by dividing and finding a remainder. Or if we're in a mod 12, we can just think about like a clock. So if it's 7 o'clock, what time is it? 8 hours later. And then that'll get us to our answer of 3.
There was one, I think on the homework that it was like 3 minus 7. Like, what do we do for that again?
Okay, so if we have something like 3 minus 7, and let's put this in mod 8. Mod 8. So mod 1 wouldn't be too much of a clock. So we're all 0, 1, 2, 3, 4, 5, 6, 7 in our clock. So I'm going to start at 3. And I'm going to go 7 spaces backwards. So 1, 2, 3, 4, 5, 6, 7. And wherever I land is my answer. That's 4.
Starting at 2. 2 is the first time you go backwards.
I started at 3,
yeah.
since that's and then I went backwards around my clock, so they're getting smaller. In a multiplication, it's probably just easiest to do the multiplication and then perform the congruence by dividing and finding the remainder. Okay? Alright.